Hi everybody. So in today's video, I'm going to be demoing how to build the Black-Litterman model, which is a very good portfolio optimization algorithm, which is based on individual inputs on how you think your portfolio should be allocated. So I have these four stocks. I call these the BOD stocks: Microsoft, Nvidia, um, Palantir, and Oracle. Let me also add Northrop Grumman. Is that their ticker? Hold on, let me see. Because I think this will be like a key factor in this portfolio. So Northrop Grumman stock ticker. Probably misspelled the shit out of that. Yep, NOC. Perfect. So yeah, so I'll get these stocks. So what I'm gonna do first is like I get a map filled with stock data. So I'm gonna do for auto tick in tickers. I will print out the length of all these stocks, so it'll be cout tick tab stock data of tick dot size and end that line. So I'll come here and compile it as g++bl.cpp sdc++ 17 and lcurl. And yes, I used to work at Giant, but okay. So /a.out. Oh yeah, there's like a slow rate limit timer on this, just so I don't get rate limited. Okay, good. They're all 260 length. So, um, what I'm gonna do is I'm gonna get rid of this. Um, I believe so. I want to make the rate of returns. So that'll be um, vector double ROR, and I also need to have a temporary vector. So that'll be vector double of TROR. So at the beginning of this, this will be TROR.clear, and then for int, or no, auto and price in stock data of tick. Yeah, then this will be TROR.pushback price, and then this will be ROR.pushback TROR. So I will come here and do printer of ROR. Let's see how this plays out. So compile it again, reset a.out. So these stocks will load again. Okay, so it's a 5 row. Yeah, we have 5 stocks by 260. Um, okay, so now what I'm gonna do is so we have the price. Maybe instead of auto price, what I'll do is int I equals 0. I is less than stock data tick dot size plus plus I. So then this will be, actually I'm going to start the index at 1. So it'll be, or actually let me just make it here. Vector double prices equals stock data of tick. So that way I don't need to like keep rewriting it out. So it'll be prices dot size, and then it'll be prices of I divided by prices of I minus 1 minus 1.0. So let me reset that. Compile it again. A.out. Import the stocks. Don't error. Okay, so we have a 5 by 259, so yeah, the rates. What I'm going to do is come here and do ROR equals transpose ROR. This time, let me just do it with... Okay, okay. So dot slash a dot out. Okay, good. So the rate of returns are working. Okay, so now we can move on. So I'm trying to think. Maybe I don't need to like um. Well, let me see. I think I think we will do different risk aversions. So what I'm going to do is come over here and define a vector function. I'll call it Black-Litterman, and the inputs will be double of um, a factor. Well, I'll call it risk, and then the vector ROR. Okay, so let me define a vector double called result, and then return result. Um, so the first thing I need to do is define the initial weights. So that'll be, actually, I'm going to need to create a function called auto vector to matrix. I'll call this v2m equals vector double, I'll call it xi. So then I will do vector double, I'll call it y, and then for auto and I in xi, this will simply be y dot push back, add the vector points to make it double, so then return y. So make that, and then I need also to make auto m matrix 2 vector. So this is going to be std vector double of, I'll call it xi again. Let me close this off. So it'll be std vector double, I'll call it y, and for auto and e in xi, y dot push back e of 0, and then return y. So yeah, these are going to be very necessary in this. So the next step I need to do is define the initial weights. So I could actually do init weights. Oh no. Yeah, init weights, and then so I will do int m equals ror dot size, and n equals ror 0 dot size. So I'm gonna go back to the 5 stock example, because now we know they can load, and I'm gonna come here and do Black-Litterman. I'll set the risk aversion to 2.5, and then just ROR as an input. So now that I got these, it's time to define the matrices that we're going to need. So it'll be pi, sigma, wm, omega, p, q, and we'll also do ones, So pi, sigma, omega, PQ. I believe this is all we need for now. So, oh yeah, and ER, expected return. So yeah, this is all coming from here. So now the next step for me to do is, let's start off by computing pi. So it'll be for int I equals 0, I is less than n, plus plus I. It'll be init weights dot push back. Actually, it probably makes more sense to just like, instead of even having to convert it, just put it right here, and then like add the double to it. So that'll be init weights is going to be 1 divided by cast double n. So yeah, that'll create it, and I also need to do the ones vector, so that'll be for int I equals 0, I is less than m, plus plus I, ones dot pushback 1.0. So yeah, that part is set now too. So from there, I think what I should do is set up a P matrix. So that's going to be the allocation. So we have the initial weights, we have the ones. We need to set up P equal to, so let's see, what stocks do we have here? So let's say we think that Northrop Grumman is going to outpace Palantir. So that'll be, oh wait, no, that's an extra 0 in here. So we have that. Let's say we think Oracle will do better than Microsoft. We could do like up to 5 assumptions. So we could say that like Nvidia is going to outpace Palantir. I'll do 2 more. So it'll be, we think Oracle. I could just do Northrop Grumman is going to outpace Oracle. And then the last one, I'm going to do 0, 0, 0. Let's see, Palantir, Oracle, Palantir, Oracle. Okay, so we have the P matrix, so 5 by 5, good. So now, so we have covariance, oh, we need the covariance matrix, okay. So in order to do that, we actually need Q, which is going to equal 1 divided by cast double of M. So this is going to be in factor. So factor of this multiplied by, so M mult of transpose ones multiplied by ROR. Okay, I think this is it. So now that I have this much, maybe I should like do printer of Q. Yeah, let's make sure there's no errors in this. Oh wow, there was a tiny little error. Pretty sure it's in here. Right, yeah. So all right, let's see what else errors in here. Result 210. Oh right, I never fixed that. Okay, so I think that's all there is to it. So yep, no errors. So I'll do reset a.out. So it's going to print out Q, which are the expected returns. Okay, so yeah, these are the average returns, average daily returns for these stocks. So now that we got that, so we got Q, that's good. The next step is to now compute. Oh, yeah, we've got P. I could just do like pi equals factor of risk multiplied by. Oh wait, no, I do need the covariance matrix. So what did I call it up here? Yeah, sigma. So sigma is going to equal. Um, so I have to subtract. Okay. This is what I'm gonna do. I'm gonna call this XMU, and then I'll declare a temp XMU. So what I'm gonna do with this is like go through. So for int I equals 0, I is less than m dot I is less than m plus plus I. So this will be temp xmu dot clear, and then for int j equals 0, j is less than n plus plus j. So this is going to be temp x mu dot pushback ROR of I of j minus q of 0 of j. And then here I'm going to do x mu dot pushback temp x mu. So now the next step is to do sigma equals m mult of transpose x mu to x mu, and then printer sigma, because we need to make sure that this is like computed. It's a very important piece of the model. So I'm gonna run it again. Okay, so we've got the covariance matrix. So pi is able to be computed. So that'll be pi equals factor of risk multiplied by sigma and init weights. But let me go back and okay. So it's init weights. Oh, I need to make this into a transpose. No. Yeah, that isn't init weights. Okay, yeah, so we do have the right dimensions, so that's pi. Now we need omega, which is going to be okay. Let's see where to start with this. So I have to do factor. Oh wait, I also need to define a tau. So that'll be double tau equals 0.05. It's just a scaling factor. So it's going to be factor of tau times sigma. So the covariance matrix. And then it's going to be m mult of this multiplied by transpose of p. So then this will be m mult of p, and then yeah, p. Okay, so this will be omega equals this. Um, okay, and then I think I need to do for int I equals 0. I is less than omega dot size plus plus I, and then for int j equals 0. J is less than omega dot size. plus plus j. So if I not equal to j, it'll be omega of I j equals 0.0. So now, so that gets the diagonal of it. So let me do printer of inverse of omega. Let's just see if like that diagonal is right or not. Um, so reset a dot out again. So it's going to load all the stocks. And the reason why I didn't show how to like import all the stocks in here is because like I've made multiple videos on it before showing how to like use boost property trees to like parse the data. And okay, so the inverse was computable. Okay, so that's good. So I don't need that anymore. So now I could like, so we got omega set. So now it's time to code this bad boy right here. So let me, let's see. So expected return, I have it listed here as ER. Um, okay, so we got pi, we got omega. So now just to do this, I'll start off in the small chunk. I will just do std vector double. I'll call this b. So b is gonna be equal to, so inverse factor tau sigma. So that's this part, and then m mult of this by pi, and then it's gonna be add same. This is gonna be m mult of inverse of omega. So inverse of omega multiplied by transpose of q, and then this is gonna be m mult of p multiplied by this. Okay, so that worked on that. So yeah, we coded this portion of it. So now I'm gonna add another one here called A, and then A is gonna equal that's very similar. Instead of being multiplied by P, it's multiplied by Q. So actually, yeah, let's look at this similarity. So tau sigma inverse. There's no pi. Yeah, I'll just manually code this out. So this will be um, inverse of factor of tau and sigma, and then there's no so yeah, the inverse of that, and there's gonna be add same, um, yeah, inverse, and then comma, it's gonna be m mult of inverse of omega multiplied by p, and this will be m mult of transpose p. So oh, this has to be transpose p. My bad. So transpose p. So we got m mult inverse omega. Yeah, inverse of omega multiplied by p. So I have to now come out here and do m mult of transpose p. And then now that I got that, I could wait, hold on. Let me just so inverse factor tau sigma. Okay. So p. Hold on. Let me just redo this part real quick. So it'll be transpose p times m mult of inverse of omega multiplied by p. So, okay, I believe we've gotten, yeah, so actually now it's going to be, so to get the expected return, we're going to do m mult of inverse of A multiplied by B. This is some intense linear algebra. Like, doing it in C++ is like, we'll know it's right if all of these weights add up to 1. So we do the inverse of this multiplied by that. So we have the expected return. And now we need, let's see. So it'll be Wm equals factor of 1 divided by risk. I'll do it as 1.0 just in case. So factor 1.0 divided by risk, multiply, so m mult of inverse of sigma multiplied by expected return, and then result equals m2 vector Wm. So now we can come down here and do std vector double weights equals Black-Litterman, and in order to check it, I'll do double total equals 0, and then for auto and t in weights. So total plus equals 1, and then I will do cout show is this right. Okay, so now let's compile this. Hopefully there's not like many errors in it. Okay, no code errors, but let's see if it's seg faults. So /a.out. So import the stocks. Five. Huh. That's weird. Oh wow, I'm okay. No. Scratch that. Yeah. Okay, that was my mistake. So what I want to do with this is basically like I will just, if this works, yeah. Let me even go ahead and like start deleting this. So what I'm gonna do is I'm gonna define a vector of risk aversions, and I'm gonna show like how those weights. Wait, what? Hold on. Weights, total plus equals t. Oh, maybe, oh, let me just print out the weights. Yeah, let me, yeah, let's see if, like, the weights are even working. It may not have, oh, maybe I might have been rate limited. Um, that's the thing. Oh, okay. So, okay. So this is what I'm gonna do. I'm gonna do std vector double, I'll call it RA equals 1.0, 2.5, and 5.0. Is that how I have it here? Yeah, 1, 2.5, 5.0. So these are going to be the risk aversions. And then I'm going to do, I'm just going to print out how much to allocate into each stock. So it's going to be So I'll come here, do for auto and lambda, I'll call it LD of risk aversion. So I'll come here, and then, so we have the weights. So I'm going to do for auto and ticker in, what do I call this up here? Tickers. Or rather, I'm just going to do for int I equals 0, I is less than weights dot size plus plus I. So it'll be cout. So I will do cout risk aversion level LD. So end that line. So I will do tickers. Is that what? Yeah, tickers of I. And then I will do weights of I. And then down here, I will do, okay. So now I will do, I'll compile it. So reset a.out. Okay, let's get all these stocks, the MIC military industrial complex stocks loaded. Okay, so, okay, I'm dumb. I forgot to do LD. Okay, so let me just reset this again. My mistake. So LD risk aversion level. So yeah, we can see like their weights allocated. So dot slash a dot out. Come on, come on, come on. Look at this linear algebra that we just went through. um, hmm. Well, um, all right. You know what I'm gonna do? Instead of like, I'll just leave the risk aversion at 2.5. We clearly like get results from that, so we're moderately risk averse. So I'll come back here, change this to 2.5. But what I'm gonna do is actually add more stocks to the equation. So I will just do for int I equals 0. I is less than weights dot size plus plus I, and then see out tickers of I, and then weights of I. Okay, so I'm gonna add Google, and I'm gonna add Verizon. So let me come up here to the assumptions matrix, and I'm just gonna add 2 zeros to these, just because we have 2 stocks. So I will make this into I'll just be like, yeah, I'll just say that these are gonna outperform the others, but you guys get the point. So it'll just be like, yeah. Okay. So this is a 7x7. We have 7 stocks. Okay. So yeah, I'm just gonna compile this. So everything is evenly weighted, but we could see that the model like uses the data to like give us the best allocation. So I'll do dot slash a dot out. Let me actually, I could probably just like drag this here now. Yeah, this is an insane linear algebra problem that we just like coded. So okay, so 28 plus 18 is 46, 58, 59. Hold on, I'm just trying to You know what? I want to make sure that this math is mathing. So I'm going to do Python 3, and then I'm going to do 0.2856 plus 0.182457 plus 0.1262 12667 plus 0.0168007 plus 0.0524563 plus 0.12675 2 plus 0.209406. Yep, they add up to 1. So yeah, that is the Black-Litterman model, and it's a pretty cool portfolio optimization model. Um, so yeah, that's how much you allocate into all of these. So it's saying like put a lot into Northrop Grumman and Verizon, but don't put so much into Palantir and Oracle. So yeah, I thank you all for watching this video. I'm going to keep coming out with more and more good content, so stay tuned, and peace out.